Hey, what's up, guys? This is Sheng here again. So today, let's take a look at 1,335 minimum difficulty of a job schedule, right? So you're given like a list of jobs, right? And in D days, you know, you have to finish at least one task every day, right? Basically, you cannot just skip that day and do nothing, right? You have to do at least one job. And the difficulty of a job schedule is a sum of difficulties of each day of the D days. Okay, and the difficulty of a day, right? So the difficulty of a day is the maximum difficulty of a job done in that day. So basically, for example, if you want to do 3 jobs in a day, right? So the difficulty for that day is the maximum difficulty among those 3 jobs. Okay, and then you're given like a array of integers, a job difficulty, and integer d, right? So the job difficulty, obviously, it means that the difficulty for each job, right? And you need to return the minimum difficulty of a job schedule, right? If you cannot find a schedule for the jobs, simply return -1, right? So here are some examples, right? So in this example, we have 6 jobs, right? And the difficulty for each job is like 6, 5, 4, 3, 2, 1, and we have 2 days to finish all those jobs. And the minimum, right? So okay, we're getting the minimum. So the minimum we need is like it's 7. Sorry, it's 7 because as you guys can see, we can split the jobs into 2 parts. I mean, we have to, right? Because we want to finish the jobs in 2 days. So where we have the first 5 jobs scheduled in the first day and the last job scheduled in the second day. That's why since for each day the job difficulty is the maximum number, that's why we have 6 plus 1, which is 7, right? And so here we have another example, So this one we have 3 jobs, but we have 4 days. Since on each day we have to at least do one job, which means that at the last day we don't have any jobs to do. That's why we return -1, right? So and then there are some like other examples here. Yeah, and here are some constraints, right? So first, so the condition to return -1 is pretty straightforward, which means that if the d is greater than the length of job, than the number of jobs, then we simply return -1. Otherwise, we'll definitely find a way to schedule all the jobs. And so how can we get the minimum, right? I mean, basically, if we have many, oops, if we have a lot of jobs here, at each day, basically, sorry, at each jobs index here, we have different ways, right? We have different ways that we can split these jobs, right? Because if we only think about the let's say at the current day, so how many jobs we can finish, right? At the current day, obviously, if we are at like at the first jobs, we have n, right? Let's say the length is n. We have n possible ways to do the jobs on the current day, right? And how about here? At the second one, we have n-1 ways of doing the job, right? To schedule the job, because we can at this current date, we can only do one job, or we can do the first 2 jobs, or we can do the first 3 until all the way to the end, or we can just simply do all the jobs on the current day. Even though that might not be a valid schedule, but we're just trying to explore all the possibilities here, right? And if the index is 2, if we're at here, we have n minus one ways of schedule the current jobs, the remaining jobs, right? That's why, the brutal force way, we have basically, we have n factorials, right? Total ways to schedule the jobs, which is definitely gonna be a TLE solution, right? Every time when you guys see this kind of n factorial thing, I think it's a strong hint that you can use DP, or you can use like DFS plus memorizations, to solve it, because this problem is like very classic examples of a 2D state, which means that we're gonna define like a DP, I and J, right? So what does this I and J means? It means that at ith job, right? At ith job and J days, remaining days, right? What's the minimum difficulty, right? Right, because if we have this two state, basically, if we are starting at this I here, it means that from I we have I to n jobs, right, left to be scheduled, and we have j days left. Okay. Then the minimum, right? Basically, the minimum number, the minimum difficulty with this kind of state is fixed, as long as we can identify this state, right? So, and that's that, right? I mean, basically, how about the state transition function, right? I mean, the state transition function will be starting from this state, right? We can pick uh the jobs from what? From I to n, right? From I to n, and between with this picked job from I to n, we can get the difficulty for the current day, right? And then we can just simply pass the remaining state into this kind of a new I, right? Like I'll say the new I, and then we have like the j minus one, right? Because this new I means the remaining jobs after picking some jobs for the current state, right? And then we just simply keep doing this until we get to the end of the job, or the end of the day, and then we just need to get the minimum out of all the minimum among all those kind of scenarios. Since we have this kind of the memorization step here, the time complexity will be greatly reduced from n factorial to a linear time complexity. All right, cool. So for the coding, let's say we have let's do an length of job difficulties, the difficulty, right? And the first, if the n is smaller than d, right, it means that we can simply return -1, because there has to be a day that we don't have any job to schedule, right? Otherwise, we just need to return the dp from 0 to d, right? So like I said, the way I define this dp is like, so the first one is the job index, right? Basically, it means that starting from the index to the end, that's the remaining jobs we need to schedule, and then we have this remaining uh, I'll call it remain days. How about that? And then I just need to add this kind of cache thing, to help us to do the memorizations given this index and the remain days, right? and the start weights, right? So we have the system's start max size because we're getting the minimum. You know, I'm also going to create a like current max difficulties, right? To maintain the current job difficulties, you know, for the DP for the current DP function. So for I in range, right? So now we just need to explore all the possible ways, right? All the possible ways to schedule the jobs for the current day. Okay. So we start from index, right? And then we end at n. That's gonna be the possible ways we can schedule the schedule the jobs. But obviously, you know, we're gonna have some invalid scenarios here, right? Because let's say we have this many of jobs here, you know, let's say we start from here. This is the index, right? This index, you know, let's say the D is 3, right? Actually, you know, the most jobs we can schedule is probably somewhere here, right? Until here, because if we include more jobs, then there won't be enough jobs for the remaining days, right? But the way I didn't handle it here is because I will handle it at here, you know, as the exit condition where I'm going to check that. But so here I'm just keeping this for loop simple. I'm trying all the scenarios from the index to the end. And then the current max, of course, is going to be the what? The max of the current max of the job difficulty, right? Of I, right? Because we need to get we want to maintain the difference, the current max, the current difficulty for different jobs selection. That's why I'm going to maintain the current max. And after that, right, I can just pass the remainings to the recursions, right? So first, you know, we have the current day's job difficulty, which is the current max, right? And then the remaining will be I plus 1, and the remain days minus 1. Right, so this is what so first I do a max because I need to get the current day's difficulty, which is the maximum of all the jobs we have scheduled for the current day, right? And after that, you know, I'm going to pass the remaining to the next state, which is going to be so first we increase the current max, and then the remaining jobs starting from I plus 1, right? And then the remaining days will be decreased by 1. So here I return the answer. Okay. So now we need to handle the the exit condition plus some of the invalid scenarios, right? So first one is that, you know, if remain equal to 0, which means that, okay, we have used all the days, right? If the index is also equal to n, which means that, you know, basically at, at the last day we have scheduled all the jobs, right? And that means that, you know, okay, cool. So we have successfully scheduled all the jobs in all the days. That's why we can simply return 0 because 0 means that it's a valid scenario, right? Else means that, you know, okay, we have reached the last day, but we still have some no, we have used all the days, but we still have some jobs remains unscheduled. Then we need to return the system max size. You know, basically the system max size stands for like invalid scenario. I think, you know, because we're getting the minimum of it, so whenever we return the system max size, this one, basically that branch will simply be ignored, right? And then the second scenario is that, you know, if the index is equal to n, right, which means that, okay, we have scheduled all the jobs still, right? But if the remain, okay, so let's say if the remain equals to 0, it means that, okay, so it's similar like above, right? That is it's identical as this one, but in the reverse order, right? Else else means that it's invalid scenarios. It's also invalid scenarios because this means that we have scheduled all the jobs, but we still have some. This else means we still have some days left, which means it's also like an invalid scenario. That's why I'm having this kind of two if statement to help me identify the exit, the valid exit condition, and also two invalid scenarios that which can be caused by this for loop. Right. Cool. So I think that's it. So let's run the code. Remain. Oh, right. Accept it. Cool. So it works, right? It passed. So now if we take a look at the time complexity, so we have what? So for DP problems, the time complexity equals to the number of state plus the time complexity to process each state, which in this case means that we have index that's going to be the n. Let's say we have n, right, and then we have d, n times d. That's going to be the total number of states. And for each of the state, we have another for loop here. So I would say it's another n, right? So which means it's going to be a n squared times d. That's the total time complexity, right? And for space, it's with this kind of top-down DP, is the space complexity equals to the number of states, which means that it's going to be n times d. Yeah. Yeah, I guess that's pretty much it is, right? For this problem, it's very classic, like 2D state top-down DP problem. You just need to figure out like this two DP state, and then a way to move from one state to another, right? And other than that, I think there isn't too much. There isn't anything else I can think of. Yep, I think I'll just stop here. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.